Hey guys, Buildzoid here, and today we're going to be taking a look at another RX 9070XT PCB. This time it's the Sapphire Nitro Plus. The PCB pictures are from Tech Power Up's review of this card, so big thank you to them for providing high-res PCB pictures in their GPU reviews. If you'd like more information about the card, there will be a link to the Tech Power Up review down in the description. And before we get into this, a quick disclaimer. This is not a review, and I'm not an engineer. I'm just some guy on the internet who likes looking at PCBs. And with that out of the way, let's get into it. Starting off with everybody's favorite high failure rate connector, the 12-volt 2x6. And unfortunately, Sapphire hasn't really done anything to address my dislike of this connector. But this is a 9070 XT, so at least it doesn't pull as much power as, say, a 4090 or a 5090 does, and that makes it much less likely for this to actually melt. I would argue it would be nice if the connector was better designed, but especially on this card, because Sapphire, like, this isn't a dig at Sapphire, but they basically took the reference PCB and replaced the dual 8 pins with one of these. Because you can see as sort of the leftovers of like a dual 8-pin power delivery design here, and they just like replaced the connector end. So what I mean by that is like we've got 2 shunt resistors. Technically, you could just use one if you're using this connector. But no, we got 2 shunt resistors. These are in parallel, so we've got like one big 12-volt plane over here, then another 12-volt plane over here. And so the shunts just bridge that over. As far as I know, these shunts should be 1 milliohm each. Also, why is this not... Oh, it's pencil. Why? Yeah. That explains that. But yeah, so 1 milliohm shunts, and those shunts are wired in parallel. I mean, literally in parallel as in, you know, they connect one big 12-volt plane to another 12-volt plane, but also in parallel in terms of the actual sensing circuitry, which is kind of interesting because I think on NVIDIA cards, they actually have individual sensors for shunts wired in parallel a lot of the time. But here, both of those shunts are being monitored just by this chip right over here, which conveniently enough is labeled U5521, which is the same like label that the XFX card had. So yeah, our 2 shunts basically connect to, actually I'm drawing that wrong. And I guess, okay, yeah, it should be something like this, where it comes through the resistor. These 2 capacitors are just for filtering. This is also a filtering capacitor. And yeah, and this chip then outputs the signal that the GPU actually uses for figuring out how much power it's pulling. So if you wanted to disable the power limit on this card, all you really have to do is short these 2 pins together. Bye-bye power limit. Or you can short like that capacitor. And I think if you do some math, you can actually scale the... Like, if you literally just put a blob of solder over these 2 legs, your power limit is gone, because the card is no longer capable of measuring how much voltage drop there is across the shunts. But what you could do, like a more intelligent thing you could do, is you could put a resistor across the capacitor or across the 2 legs. It doesn't really matter. And then you could calculate the appropriate resistance to get like cut the power reading in half type deal. But off the top of my head, I don't know what value you would need to use for that. I think these are 10 ohms, and then there's like a calculation you can do to figure out what value would be appropriate. Personally, I just put a blob of solder because I don't want to power limit. And I don't really care about having working power readings. So anyway, that's the shunt monitoring on this card. Now, one thing I do like about sort of the input of the power on this card from Sapphire is that we do have fuses for 2 separate internal 12-volt power rails. Now, I'm not sure how those are actually distributed around the card, because this is a multi-layer PCB and this is a photo. I can't exactly see where things are connected. But my guess would be that the power distribution on this card is something along the lines of this, like this fuse and this inductor are for this side of the PCB, and this fuse and this inductor are for this side of the PCB. Now, my one issue with that thought process is that we do have, actually, I guess it could be, this could also power the memory, and that would mostly solve that, I think, because then you'd have 1, 2, 3, 4, 5, 6, 8. Wait, that doesn't work. Oh no, it is 6, 8, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay, so that would actually probably work out to be relatively balanced. I mean, technically the two memory phases probably output less current than the two memory power stages over here, but should be close enough, I think. So, yeah, and the thing I like about this is that we have fuses and they're actually effective, because one of my other complaints for this connector is on a lot of cards, it ends up being just a unified 12-volt distribution for the entire card, which then means like, okay, so, you know, you have like a 600-watt card, and then when you try to put a fuse on that, you don't want a fuse that's going to pop if the card pulls a little bit over 600 watts, because that might happen under normal operation. So then you need like a 70 amp fuse or a 60 amp fuse, right? Actually, it's 60. Yeah, that would give you a 720 watt fuse limit. Now, the thing is, a 60 amp fuse, if one of your power stages dies, is not really going to do anything. Like, there's a decent chance your power supply's overcurrent protection is going to kick in before that fuse burns out. So that's useless as far as I'm concerned. And one of my one of my complaints for a lot of NVIDIA cards. Here, on the other hand, we have two 20 amp fuses. At least I'm pretty sure these are 20 amps. I'm not 100% on the letter codes. But anyway, so we have two 20 amp fuses, which I'm just judging that off of the fact that's usually what you get on like a single 8-pin connector is you get a 20 amp fuse. So these should be 20s. And that means if one of the power stages blows, hopefully the fuse will blow before the power stage manages to like weld itself to the board or, you know, kill the GPU. So I do appreciate the fact that because Sapphire has the like split 12-volt delivery on the card itself, which I'm relatively certain is just a leftover of this originally being a dual 8-pin PCB. But it does mean that we do have some extra, like we have fuses that improve the repairability of the card, and I appreciate that. Note that I said repairability, not reliability. These fuses aren't here to prevent failures, they're to minimize damage in case of failure. So, like, if the card fails under warranty, these don't really do anything for you. If they fail outside of warranty, they increase the probability that somebody's going to be able to fix the card. So anyway, I do like that. And then I guess we'll talk about the other input filtering stuff when we get to the major power delivery stuff. So let's talk about minor voltage regulators around. Actually, now let's first address, does this card have dual BIOS? No, it does not. And I don't like it because this card is relatively expensive, right? This is one of the more expensive 9070 XT models. They have the padding for that BIOS switch. They just didn't populate it. And if you look at the back of the card, you can see that they even have the padding for the extra BIOS chip, which they didn't populate. And the thing is, BIOS chips and switches aren't very expensive, so I am really not impressed by. For a card this expensive, I think they could have, you know, added an extra BIOS chip and a switch. I mean, technically, there's also some passive components that it would have needed, but those, relatively speaking, don't cost anything, right? They're going to cost a fraction of what the BIOS chip costs. So, yeah, I'm not really... Like, for a card this expensive, I think it's kind of lame. Even though with modern AMD GPUs, there's not really much you can do as far as BIOS flashing goes, I do think it's kind of lame that they didn't include dual BIOS. So, because it is just, yeah, like, it's just kind of lame. Below that, we see the remains of what used to be a 5-volt regulator that isn't populated. Then here we have a 5-volt linear regulator that isn't populated. Interestingly enough, this card has no shunt on the PCIe slot. We do have a fuse. It's a 20, which I'm not a fan of. I think the fuses for the PCIe slot should generally be 10 amps and no more than that. Yeah, this I'm pretty sure is a 20. Now, funnily enough, I think the reason why there isn't a shunt resistor for monitoring the power consumption from the PCIe slot, right, you can see there's nothing on the back either, is that this card doesn't run any of its more significant voltage regulators off of the PCIe slot at all. So I kind of suspect that the only thing that this is powering might be the fan headers. Not 100% certain about that, but that would make sense to me. And yeah, so I think what's going on is like these voltage regulators, like literally everything just runs off of the 12-volt high power over here. And the PCIe slot just kind of like exists. So yeah, that's kind of cool, I guess. I don't know. I'm kind of indifferent to this. It's not like you're going to be stacking 4 of these into a system, so how much power it pulls from a PCIe slot doesn't really matter, in my opinion. Anyway, where was I going? All right, 5-volt regulator, LDO. We do still have a 5-volt regulator, of course, because we have a 5-volt RGB header over here, so 5-volt has to be present on the card somewhere, and that's this right here. So, yeah, interesting. Well, it's not really an interesting choice, but, like, yeah, just a choice Sapphire made. They have one big 5-volt regulator instead of multiple smaller ones, and then you can see that, like, we have a fuse over here for 2 HDMI ports. You can even, like, sort of see how that power delivery for those ports goes. And so that fuse is ultimately going to be connected to this thing over here. You obviously also have a fuse for the RGB header, though it kind of looks like this might be connected to ground, which doesn't really make a ton of sense to me, but I don't know, maybe that's just like a way to do RGB headers. And there's more fuses, like there's another fuse over here, though I'm not sure if this one's for 5 volts or something else. Might be for 5 volts. There's another fuse right off the actual 5-volt regulator itself right here. Because, yeah, you don't really want... I mean, I think if this one gets tripped, the card probably won't run anymore. Because I'm pretty sure this one's right off the inductor, so you're not... Like, if whatever circuitry needs 5 volts on this card is not going to get it after that trips. Yeah, so we have one 5-volt regulator with a whole bunch of fuses connected to it. There's another one up here, but I'm not entirely certain that this one is for 5 volts. This one could be for something else. Anyway, so yeah, 5-volt regulator over there. And over here, we've got our 1.8 volts, 1.2 volts. Now, 1.8 volts, this one, I think might just be for the BIOS chips and maybe something inside the core. What I find super confusing about the 1.8 volt regulator on this card is that this right here, as far as I know, is a linear regulator that also produces 1.8 volts. What I find really confusing about this is like, but we already have a bigger, better 1.8 volt regulator right here. So yeah, why does this exist? I have no idea. But based on the labeling of the Asus TUF card, this seems to be the 1.8 volt VPP for the memory chips. Which really, like, I don't think BIOS chips need an entire switching regulator just for themselves, especially when it's like one BIOS chip. I mean, if you have 2 BIOS chips, they don't run at the same time. So, like, yeah, like, I don't, like, I'm assuming this also powers something inside the core, but I don't know what. And on some cards, this will also power the VPP rail for the memory chips, but on this card, that seems to be handled by this linear regulator-looking thing over here. Yeah, so that's a mystery for me, is like what is going on with the 1.8 volt supply on this. Then we've got 1.2 volts, which goes to the core, and I don't know what it actually does, but it's for the core. So, yeah, and then down here we have 0.77 volts. Same situation, goes into the core. I don't know why the core needs a 0.77 volt rail, but it does. You'd have to ask AMD what they're doing with like all of these smaller power rails. Anyway, the voltage regulator for all of these is from GS Tech, and it is a GS9216. And this should be a 12 amp integrated buck converter, which I don't know if that's overkill or not, because I don't know how much current the core actually pulls on these power rails. It probably is, as I don't think most cards even bother putting heat sinks on this chip. So, yeah. Anyway, so that's our minor voltage regulators. Now let's talk about the big ones that I do know stuff about, or at least know more stuff about. So, we've got VDDCI, VSOC, and then VCore. So we'll call this VCore 2. Because, yeah, we're going left to right. Even though it does, well, it doesn't really matter. Wait, did I over... Oh, I overdid it. Oops. Yeah, I got mixed up. SOC, VDD, I'm going to use lowercase. Makes it easier. And then VCore. All right, and then on the other side, We got more SoC and more VCore, but no VDDCI. So and then, of course, up here in the middle, we have the memory power rail, which I like to call VMEM. Anyway, so that's our main power rails. VSOC, okay, how should I do this? Well, whatever. They're controlled by these two chips over here. These are both monolithic power systems, MP2868s. The bottom one is running in a 3+2 phase configuration where it's running SoC plus VMEM. And the top one is running in 5+1, so this one's completely maxed out. This is one of the reasons why you don't see 9070 XTs with more than 10 power stages for VCore, is that there's not really an easy way. Actually, that's not true. You could put 3 power stages into each phase, but yeah, that's not super popular. Funnily enough, there are motherboards that do that. But anyway, this one's running in 5+1. And that's our VCore plus VDD CI. What I kind of appreciate with Sapphire's PCB layout here is it's super easy to see the current sensing circuitry. Like you can see, like phase. Actually, I don't think the phase order is 1, 2. It's like alternating order. Last time I measured it, or actually, it was alternating order. In like this one was like this. The next one after that was like all the way on the other side of the board, but it doesn't really matter. The point is you can see the 5 current sensing circuits, or like the input filtering capacitors for the 5 current sensing circuits for the 5 VCore phases that we have here. And in terms of how these phases are actually set up, these 2 power stages are just wired to the same PWM signal. So they switch on and off at the same time. And that's why technically if somebody really wanted to make like a 15 power stage 9070 XT, they could. You could just put 3 power stages into each phase instead of just 2, but Sapphire opted for just 2. So the phases are split up like this. So we got 3 on this side and then just 2 on the other side. Now, the reason why the VCore power rail and technically the SoC power rail is doing the same thing is split up like this around the core is because it means you effectively get a wider cross section in your power plane, which reduces the resistance, which is nice, as well as like inductance somewhat. So that improves power delivery effectiveness to the GPU core. Same thing going on with the SoC power rail, as you can see, pushing current from both sides. Now, with the SoC power rail, it's less important because that's like a lower current rail. Now, one thing worth noting is because this has, 3 phases on this side and 2 phases on this side, the current distribution between the 2 power planes is not going to be completely even, right? You're going to have 3/5 of the total core current coming from this side on average, and then 2/5 from the other, but that's still better. Well, that's still perfectly acceptable. It's not really going to make much of a difference, right? It's not a huge difference between the 2 sides, and also it really depends on like the actual design of the power planes themselves. Like this one could be a bit wider, and then it can carry more current anyway. But yeah, so that's kind of the layout that we've got going on. And how the VRMs are controlled. So now let's talk about the power stages. And Sapphire opted to just keep using the MP87. Actually, we're going to go over here. There's more space. So the power stages are from Monolithic Power Systems, and they're just MP87993s again. These are 50 amp smart power stages. So they integrate temperature, like over temperature protection, over current protection, and some other safety features as well. But to my great surprise, I managed to actually get some documentation for these, which unfortunately isn't public. And they're a lot less efficient than I thought they were. In the previous video about a 9070, I used the documentation for an MP86992, which is also a 50 amp power stage from Monolithic Power Systems. As it turns out, the MP86992 is a lot more efficient than these are, even though they're both 50, like nominally 50 amps. And this is one of the issues with the nominal current ratings for power stages is depending on who the manufacturer is, what their measurement methodologies are, you don't really know. And even with sometimes for the same manufacturer, like you don't know if it's like, is it nominally some current because it's really efficient, or is it because they expect you to put a bigger heatsink on it, right? Also, an interesting thing about these is these run on 3.3 volts. They don't need a 5-volt rail, which is really interesting to, well, it's not really that interesting. Like 3.3 volt power stages have been a thing for a while, but I haven't really, they're not super common on motherboards and stuff until now, I guess. Because basically every single 9070 out there uses these power stages. I think all of the 5090s also use these power stages. So yeah, these just kind of showed up. Super popular, but surprisingly not that power efficient. So yeah, let's talk about like heat dissipation estimates for this card. Now, we do have 10 of these power stages, and we're assuming an output voltage of 1 volt, which is actually pretty close to the operating voltage. Now, technically, there's not actually going to be 1 volt at the power stages, because you do have voltage drop across the power plane, so the output voltage at the inductors is probably going to be closer to like 1.1 or something, and then by the time it gets to the core, it's going to be 1 volt-ish. And the actual efficiency ratings are not, are not accounting for that power loss in the power plane itself. So they're also not, so technically, because the output voltage at the inductors is going to be higher, the efficiency would be worse. But also the inductors assumed for the like data sheet spec is 220 nanohenries, which probably have more DCR than these do. DCR being like direct current resistance. These are 150 nanohenries, which these are like low inductance inductors are kind of wild because they're basically just a strip of wire with some core material around it, which is kind of funny to think about how that's like a, like that a component can be so simple and yet be like really important. Because if you just like if you replace the inductor with just a strip of wire, you'd be in big trouble. So, yeah. But anyway. So 1 volt and 400 kilohertz switching frequency. But the point I was trying to make is that these are estimates. They're not super accurate, but yeah. Anyway, so 150 amps output current. The power stages here should produce about 12 watts of heat, which is perfectly acceptable, but this is also less current than the card regularly draws under normal operation, so that's not really that useful, unless you're playing some very old games and the card isn't running at full tilt. Now, 200 amps output, this would be like more like 9070 territory rather than a 9070 XT, but we're getting closer. About 18 watts of heat output. Still very manageable for a VRM like this. Like basically anything less than 2 watts per power stage is not really a cooling concern. Unfortunately, a 9070 XT, especially one where you can raise the power limit quite a lot because, this one does have the 12-volt 2x6 connector, so it doesn't... It's basically like a triple 8-pin card in terms of the kind of power limits that you can set. Yeah, 250 amps, about 25 watts of heat. But then again, this is a GPU. The VRM has a heatsink, and there's a fan pointed directly at it. So this is not going to be an issue. But yeah, compared to some motherboards these days, this is not really that impressive. Then we get up to 300 amps output current. And at that point, this VRM should be producing about 35 watts of heat from the power stages. Still very much manageable, but you do need the heatsink and you do need airflow. 350 amps. Now, I'm not sure if this card has the same current limit as the reference PCB, but the reference PCB for the 9070 and the 9070 XT has a 330 amp current limit on the VRM. So you wouldn't be able to reach this without bypassing the current limit somehow. But if you did, at 350 amps, this VRM should produce about 47 watts of heat, which is still manageable. It's just, yeah, kind of a lot. And then 400 amps output, about 61 watts of heat. Now, luckily, I think the only way you'd be seeing this kind of current output is if you're running like benchmarks for like scores rather than sustained load, because this die is extremely hard to keep cool. And like it's already extremely hard to keep cool before you even get to the 300 amps output territory. So yeah, this is very much like you're probably looking at sub-zero cooling in order for the card not to just thermal throttle the entire time. That's like the other fun thing is like if the chip overheats before the VRM does, you don't have to be concerned about this. So yeah, if the GPU core starts thermal throttling before the VRM starts thermal throttling, you don't have to worry about the VRM getting overloaded. But yeah, so this is like if you watch my previous 9070 video, this is not going to look that impressive in terms of efficiencies because again, in the previous video, I was using numbers from the MP86992, which I incorrectly assumed would be close enough in terms of performance to the MP87993. But as it turns out, the MP87993 is a lot less efficient than the MP86992 is. So that makes it a really good thing that Sapphire actually put 10 of them here instead of just 8, right? Because the reference PCB for the 9070 and 9070 XT does just have an 8 power stage VCore rather than a 10. Now with the 10, I think this is great. I mean, well, I don't think this is great. It's not like it's massive overkill, but it's fitting for the card. So I'm not going to complain about it too much. And also, like I mentioned, cooling one of these before you even reach 300 amps gets really difficult. So, yeah. Anyway, so that's the VCore VRM in terms of current handling capacity. The SoC VRM is just a 3-phase. I've experimented a little bit with adding voltage to the SoC power rail. It doesn't gain at all, so it doesn't really... Like with the SoC power rail, it's not like the core power rail where the more power you shove into the card, the faster it gets. The SoC power rail kind of doesn't do anything from a performance perspective. Though, interestingly enough, if you overclock the memory, at some point, the AMD's own driver will automatically up the voltage on the SoC power rail. So at stock clocks, I believe it's 0.8 volts, and then if you overclock the memory, at some point it'll go up to 0.85 or I think 0.9, something like that. So that's kind of interesting, but the SoC power rail uses the exact same 50 amp power stages, and because you're not going to be pushing the SoC power rail, well, anywhere, because it doesn't go anywhere, I see nothing wrong with that. It's not like the VCore power rail where, like, yeah, if you had more cooling, you would potentially, you know, get into this territory. With the SoC power rail, I don't like... It doesn't seem to help anything, so I don't see a reason to complain. VDDCI, same thing. As far as I can tell, actually, I think the card got worse when I tried to improve, raise VDDCI. I think it just made the memory controller really upset because this is basically some kind of memory controller power rail. It's not the PHY itself. The PHY itself is going to be powered by the main memory power rail because you want the memory chips and the GPU talking to each other with the same voltage. But the memory controller should run off of VDDCI, and yeah, it doesn't seem to appreciate having VDDCI raised or lowered. So yeah, that single MP87993 is plenty for that. Then the memory power rail, same thing. I tried overvolting the memory. It did not help. It made it worse. So what's interesting, though, is like when I say it made it worse, and I tried also undervolting the memory, and that also made it worse. But yeah, the interesting thing is because these cards have error correction, if you give it like more voltage than it likes, score goes down. If you give it less voltage than it likes, score goes down. You basically do anything that the memory system doesn't like, and instead, like, well, if you push it too far, it will crash. But if you just push it a little bit outside of its preferred operating parameters, you just lose a bunch of performance. I mean, well, you first start losing a little bit of performance, and then it gets progressively worse until it crashes. But yeah, so the memory power rail is 2 more MP87993s, and because there's really nowhere to push the memory to that I've found so far, I don't see any problem with that. So yeah, from like an overclocking perspective on the 9070 XTs, the only thing that really matters is the VCore VRM, because as far as I can tell, nothing else actually scales with voltage. So yeah, and like increasing the memory clock does slightly increase the power consumption, but not enough to like need more substantial power delivery. So yeah, is there anything? Trying to think. Oh, I guess I should have mentioned the SoC. I don't know for sure what the SoC power rail powers, but I'm guessing it primarily powers things like the L2 no, the Infinity caches, as AMD called it, which I guess would be like an L3, wouldn't it? But yeah, that's what I'm assuming. And then the like Infinity Fabric interconnect that the GPU has internally should also be running off of the SoC power rail. But anyway, so yeah, that's the like power delivery in terms of like how much current it can deliver. Let's talk about capacitors. Now, this is actually, yeah, so I actually really like what Sapphire has done in terms of capacitors with this card. It's not really super obvious from the front because this doesn't really look that different from a reference PCB for input filtering. And I'm not 100% certain about this. Am I blind? 1, 2, wait, did I not count these? Or am I just stupid? 1, 2, 3, 4, 5, 6, 7, 8. Wait, what? That's it? Oh, it is 8. Oh, okay. Yeah, I'm just stupid. So we've got these 4. Wait, that's not 4. I don't know. This shape is just like messing with my head. Anyway, so these 2 and these 2 should be the input filtering for this. Well, these are obviously input filtering for this side of the card, but I'm assuming these 2 are also part of that. And then these 4 are going to be input filtering for this side of the card. And this like split input filtering setup with the bulk capacitors, like this is fine. It doesn't like these have so much ESR and equivalent series inductance, so equivalent series resistance and inductance, that it kind of doesn't matter where you put them on the board as long as they're not before the input filtering inductor, because that is obviously an inductor, so it has a lot of inductance. But yeah, so like having your bulk input filtering capacitors just like in kind of like really far away from the components that they're actually filtering really doesn't matter because these are really slow. So yeah, but we do have 4 of them for each of the 2 12-volt power rails that the card has. So 8 in total, which is what you find even on like a reference 9070 or 9070 XT PCB. So Sapphire isn't really changing anything there. And for output filtering, for VCore, we've still got 10, which actually, like, the layout is a bit awkward. I think it's like this. Yeah, because the SoC, like, VDDCI has these 2 capacitors for itself. SoC has these 2. So like that. Then SoC over here, does it have 2? This is extra, I think. Yeah, so, yeah, we've got 2 more here. And then these 5 are VCore again. And all of this is like standard 9070 reference PCB stuff, right? So the VCore filtering is made up of 10 820 microfarad like aluminum polymers in a cylindrical package. These are made by APAC. That's that logo over there is. And that's a Taiwanese manufacturer. And you can also see that they're rated for 5,000 hours at 105 degrees Celsius. Though I personally don't really care much for endurance ratings on aluminum polymer capacitors because in my experience, they kind of last forever. I have like 15-year-old GPUs and the capacitors on them are still fine. So like, yeah. And those, a lot of the time, like back then, a lot of the time they would use like 2,000 hour rated capacitors. Whereas these days, the 5,000 hour rated capacitors have become the default for most motherboards and GPUs. So yeah, like if the 2,000 hour ones work just fine after 15 years, I don't really see a reason to be concerned about 5,000 hour capacitors on brand new GPUs. So yeah, but we do have 10 of them. They are 2.5 volts, which makes sense because, you know, this is a low voltage power rail, so it doesn't, like, you don't need a high voltage rating for the capacitors. SoC is made up of 4 820 microfarad caps. which again, actually, I think this might be one more capacitor than you get on a reference PCB, and then VDCI is made up of 2. I will point out, though, that the SoC power rail is surprisingly noisy. I do have, like, I ended up hooking up the oscilloscope to just every power rail. Well, okay, I didn't hook it up to these 3, because really don't care about those. But, yeah, so the SoC power rail is, like, surprisingly noisy on a reference 9070 PCB. At the same time, though, the SoC power rail doesn't seem to affect overclocking much at all, so it doesn't really matter. And the same is true for VDDCI is not that noisy, but also doesn't really affect overclocking in any way, shape, or form. So, you know, yeah, you don't need anything special for power filtering. Now, the VCore power rail is also really noisy. And the reference design of just having 10 820 microfarad caps, in my opinion, is a little bit inadequate, and the core clock does scale with voltage. So better power filtering for the core is a good thing from an overclocking perspective. It doesn't make a huge difference. It's not like the card is non-functional if you only have 10 800 microfarad capacitors. It's also not like you're massively worse in terms of overclocking if you only have 10 820 microfarad capacitors. But I do appreciate the fact that Sapphire slapped on these 8 surface mount aluminum polymers. Now, I don't know who makes these. I think these might also be made by APAC, but I'm not 100% certain. And the reason I'm not 100% certain is because there's no logo on these. And I'm actually not even sure if these are aluminum or tantalum. They could be either. But the benefit of these rectangular capacitors compared to the cylindrical ones is just due to the physical shape and how they're manufactured. They have less equivalent series inductance, which is very helpful when you're trying to filter like fast transients from a GPU core. Because, yeah, the core power rail on a 9070, very noisy. So I like these. I'm not sure how much of a difference they make, because obviously I don't have the card in hand, so it's not like I can take a comparison measurement between a reference design and one of these. But they should help. And other than that, Sapphire has also added a bunch of ceramics, though they also left out a lot of them. But it's still more than what you get on like the bare minimum configuration of the PCB, so I do like that. Yeah, but you can see like on the SoC power rail, it's just like, yep, those are optional, and they did not populate them because, yeah, they don't affect overclocking in any way, shape, or form. So it makes sense to just kind of leave them out. Or at least that's my guess currently, is that, because I haven't tested, like, I know for sure that raising the average voltage or lowering the average voltage doesn't help. Improving the voltage regulation, I'm assuming, is probably also not going to help for the same reason. I could be wrong about that, but I haven't tested that theory yet. So, but I'm assuming that like more capacitors on SoC or VDDCI just isn't going to help the memory overclock at all. So, yeah, and a similar thing is going on with the memory filtering itself, right? We just have 3 of the, I don't know what they are. They might be tantalum, might be aluminum polymers. And then you can see that the optional ones got left out. And then also some of the ceramics got like left out, which, yeah, like my thoughts on this are basically like, if it doesn't negatively affect the overclockability of the memory, then yeah, it doesn't make sense to include those extra capacitors, because, you know, as long as the memory chips are getting voltage within their, like the power supply to the memory chips is within their tolerances, then like, who cares? Yeah, so that's the capacitor configuration, and basically I like what Sapphire has done in as far as like adding extra filtering to the VCore power rail. The other power rails, they haven't done anything, but I also don't see any reason for them to do anything, so that seems completely reasonable to me. And I think that's kind of it for this card. So yeah, my one complaint for this PCB from Sapphire is just like, man, why you gotta go use this connector? Actually, there is one upside. If you have a card with multiple 8-pin power connectors, it's more work to disable the power limit because you need to, like, instead of just having one U5521, you have like a U5521 and then a U5524 and a U5525, and then, like, you'll basically, instead of having one shunt monitoring chip, you're going to have 3 of them, one for each of your power connectors. And actually, if you have a triple 8-pin card, there's going to be 4 of them because there's going to be one on the PCIe slot. And then you need to short all of them out. And the thing is, if you just have one of these chips, what you could do, if you want to be fancy, is you could wire this to a switch. And then you have the option to switch the power limit on and off, right? I mean, I'm not sure where exactly you would find space on this board to add the switch. But yeah, you could totally add a switch to the card so that you can switch the power limit on and off. I have something like that on my 4070 Ti in my daily system. I don't use it because it doesn't help performance, but I do have the option to just turn off the power limit on my 4070 Ti whenever I feel like it. And that's the one upside with this power connector, is makes that modification very easy. But or like makes it very easy to have a switchable power limit, because otherwise you need like a switch per shunt monitoring chip, because you can't just wire them all into one switch. That doesn't unfortunately work. So yeah, but I do like, so basically I am not, like, the thing is, I'm just generally not a fan of this connector. I don't think on a 9070 XT it's as much of a problem as it is on a 5090. But I still don't like this power connector. The rest of the card, I do like it, except for the lack of dual BIOS. Yeah, it's just, like, I get it. BIOS flashing AMD GPUs these days is not really that useful, but, like, BIOS chips aren't that expensive. So, yeah, as far as the power delivery is concerned, I like the upgrades that Sapphire has made to the VCore power delivery, right? We got more power stages, more capacitors. I like both of those, and then everything else is basically the same. Actually, yeah, basically the same as what you get on the reference card, which I don't see any issues with. Like, there's no point upgrading things that don't affect the overclockability of the card and are already perfectly functional. So, yeah, that is it for the Sapphire Nitro. So thank you for watching. Thank you to Tech Power Up for the PCB pictures in their reviews. There will be a link to that review in the description. If you'd like to support the channel, there's a bunch of links in the description that you could check out. That would be very much appreciated. And that's it for the video. So thanks for watching, and goodbye. Oh no, where's the stop button? There we go.